Well, SIMCA stands for Soft Independent Modeling of Class Analogies. And the basic idea is, again, simple. It's a PCA-based method. But instead of using scores, instead of applying PCA for observations from all classes and then use scores to discriminate the observations, what we do here, we take only objects that belong into a particular class, and then we make a PCA model that describes the behavior of these objects in full. And then we use this model as a basis for classification. So that means that SIMCA is one class classifier. So you need as many SIMCA models as many classes you actually have. And then the implementation is very simple. I mean, most of the steps you see here is just a PCA model. So first of all, we need to build a PCA model. We use training set for that, but only objects from a particular class, only members. Yeah. And then we choose optimal number of components. We compute critical limits for the objects, and then we also need to define. We compute the distances, the score distance and orthogonal distance, and then we also need to define critical limits. That's what PCA does, actually. We also did it in PCA, right? So that's the PCA part. This is simply building a PCA model, right? And then we have a new object. What we do, we project this object to this PC space that we already created, and then we simply compute the score and orthogonal distance for this object, and we compare this with some critical limits. We will discuss details in a minute. If these distances are small enough, we accept it. If these distances are large, we reject it. So that's the basic idea. So strictly speaking, SIMCA is a way to identify extreme objects in your PCA model, or outliers if you want. Okay. Now let's recall what the score and orthogonal distances are. You remember that when we build a PCA model, first of all we project objects to this model. So we have a projection, we have an object itself, right? And then we can measure two distances. The first distance is called orthogonal distance. It's a distance between the object itself and the projection. And this distance is orthogonal. So we use, for example, Euclidean distance to compute it, right? The second distance, it's a distance between the projection of this object and the center of your model. So it's called a score distance because you compute it in the score space. And you remember, actually, we need to compute it as a Mahalanobis distance because of the different variance along different principal components, right? We discussed this in PCA, but the idea is similar. So it's a measure how far your object is from the origin inside the PC space. So this is an example I also showed you in PCA part, right? So we have an object here, and then this part will be orthogonal distance, and this will be a score distance. But we also, if you want to calculate the score distance, you need to normalize the scores first, standardize the scores first, right? And the reason why I use a square root here and a square root here is because we use h and q to denote the squared distances. It's just makes your life easier when you work with squared distances, and then you don't care actually is it negative or positive. You do care only about the overall distance, right? How big is it? So you can see that when we want to compute the orthogonal distance, we simply take a sum of squared values along rows of matrix E. And then when we compute the score distance, we take this matrix T. And then we first of all, we standardize columns of matrix T to eigenvalues. It's a variance of scores, right? So we make a variance, unit variance. So it's like standardization of scores. And then we compute distance just by summing up squared values of the rows as well, right? So this is how to compute a score distance. And then we know in advance that both distances are simply a sum of squared values, right? So we can use, for example, chi-square distribution for describing behavior of these distances. Okay. And then we can also define critical limits. We will talk about this later. We define alpha. First of all, it's a significance level. And you remember in PCA we told about alpha is how many extremes we expect to see. For example, if alpha is 0.01, it means it's 1% of values will be considered as extreme, right? And then we have two limits. One is for this one dashed line is for extreme values, and then one is for outliers. That's what we did in PCA, right? Now let's talk a little bit more about that. First of all, what you see here, it's a distance plot made for Gaussian noise. So it means I just generated a lot of random values using normal distribution, Gaussian distribution, and then I did PCA and then created this distance plot. Then you remember we can also use logarithmic transformation for this plot, but it's not the thing I want to discuss. The thing I want to discuss is these orange objects. You can see that all these orange objects were sort of outside the limit. In this case, I use one limit here. So they are considered as extreme, right? And that's the overall idea of SIMCA. All objects that are considered as extreme should be rejected by the model. So it means that alpha, it's a percent of false negatives. You remember what is false negative? Is when models say no, but the object belongs to the class. So in all these cases, orange objects belong to the class, but the model rejected because they are outside the limit, right? So it means that alpha, the significance level that we use for building these critical limits, is a expected number of false negatives. So we can actually define the number of false negatives in advance, right? What about false positives? We cannot do anything about false positives here because SIMCA is one class classifier. So it means that we don't use objects from the other class to build the model. But there are some peculiarities which we are going to talk about about later. Okay. So SIMCA is one class classifier, and apparently the most important thing, actually two things are very important. It's how many components to use and also how to define the critical limits, right? If you have more than one class, then you build independent models. So it means that you don't take into account, for example, that's a class 1. And then you can see that I used two principal components, right, for building a class 1. So I've done with this, so now the model is fixed. Now I got to class 2, and then I don't care what happened to class 1. I just now built another PCA model independent from the other classes. So that's why there is a word independent in SIMCA, right? So in this case, you can see I also use two components, but they are oriented in a different way, right? Then I use class 3. Again, it's independent from class 1 and class 2. And in this case, you can see I use only one component. So number of components in SIMCA models can be different because they are completely independent. However, all these models, as well as all these objects, they share the same variable space, right? So what it means? It means that if you have more than one SIMCA model, you can measure a lot of interesting things. For example, you can measure distance between models. You can measure, for example, which variables are responsible for the discrimination between models and a lot of other things, right? But let us concentrate on one class only so far. Now let's talk about how to actually calculate the critical limits. The original paper that was published by Svante Wold and Mikael Sjöström, it's paper like this, and then they proposed to use F distribution and also the Hotelling t-squared distribution to define the limits. But nowadays we use different ways. First of all, we know that it's a mostly chi-square distribution that we can use for both distances. And then there is no one fixed rule how to compute critical limits for that. There are several ones. I think about 4 or 5 currently existing on the market. And by saying on the market, I mean the following. It depends on which software you use. Different software, usually they use different ways to compute critical limits. A very nice overview of these decision rules in SIMCA, how to compute critical rules, was recently published in Journal of Chemometrics. I highly recommend you to read this review first. Okay, and then there are, strictly speaking, two kinds of decision rules. Either you treat every distance individually, so it means that you compute a critical limit for orthogonal distance, then you compute a critical limit for score distance, and then you define your rule, accept or reject your object by comparing these individual critical limits, right? So in this case, of course, we have one small problem. It's called multiple comparison problem because you need to run two tests to make one decision, to test one hypothesis. So it means that you have this risk of type 1 error higher. And then you need to use, for example, Bonferroni correction or similar things from statistics. Anyways, rectangular rules are still popular. You can find them in many software. Another way to do that is to combine these two distances into one and then compute a critical limit to one distance. In this case, you have only one limit, so it means that, for example, if you make a distance plot, it will be just one line instead of two lines, and that's why it's called triangular rule, because here you have a rectangle for the acceptance area, right? And here you have a triangle for the acceptance area like this. Okay. So let me show you an example how you can compute actually critical limits both for rectangular rule and triangular rule, right? So first of all, let's recall the distances, how we compute the distances, and also recall that these distances is a sum of squared values. And we know from statistics that sum of squared values, if these values are follow normal distribution, the values themselves, not the squares. And then if they actually have a unit variance, then they follow a chi-square distribution. So it means that if we take a computed value, q, and then if we normalize it or standardize it by using certain factors, then this normalized value or standardized value it follows the chi-square distribution with a certain degrees of freedom. So nq, it's a degrees of freedom here. And then the same idea for the score distance, right? If we take a score distance, it's a sum of squared values. We need to standardize it somehow. And then if we standardize it correctly, then it will follow the chi-square distribution with these degrees of freedom and h degrees of freedom. Yeah. How to compute degrees of freedom? Well, there are again different approaches for that. And one of the approaches called data-driven approach is that we compute it as we estimate any other statistics. For example, how we can estimate average value, right? We simply take our sample, take a sum of values, and then divide to n. So that's the estimation. So we can estimate these two statistics as well by using the real distance values computed for the calibration set. And this is how. The scaling factor Q0 is just an average distance. Okay. And then the degrees of freedom is computed as follows. You take a ratio between average and standard deviation, square it, and then multiply to 2 and take an integer part. So you round it, strictly speaking, right? And then you can see the same idea for the second degrees of freedom. That's it. As soon as you compute it simply based on your distance values, now you can use a chi-square distribution. For example, how to compute a critical limit here. You need to use inverse distribution function for the chi-square, and then you need to provide the significance level. In this case, you need to provide 1 minus significance level because we compute a limit for accepting, right? So 1 minus alpha and then nq degrees of freedom, right? For example, in R, you use the q chi sk function. That's exactly inverse CDF function for chi-square distribution. And then, for example, if you have alpha is 0.05, so you expect 5% of false negatives. So here you have 0.95 and then nq, right? So that will be a critical limit for this scaled value, right? And then the same here. So to compute critical limit here, you just take minus 1 minus alpha, and then nh here. Right? Remember that this alpha, because if you want to use a rectangular limit, then you need to correct alpha using Bonferroni correction. So instead of 0.05, you need to use 0.05 divided to 2. Recall Bonferroni correction if you forget what is it. Okay. However, we can also use this to compute a triangular rule. In this case, we combine these two distances together, the scaled distances together. So you can see this is a scaled q distance, this is a scaled h distance, and then we simply take a sum of these two distances. We know from PCA that when we add more components, the q distance becomes smaller and h distance becomes larger and vice versa. So these distances actually relate to each other, right? The result we'll call a f distance, and it's also followed chi-square distribution with nf degrees of freedom, and nf, it's a very simple thing. It's just a sum of nq and nh. Okay. So in this case, you need to use ICDF function for this, for example, 0.95 if we talk about 5% significance level, and then nq plus nh. So you will have only one critical limit in this case, right? And then since it's only one critical limit for combination for sum of these two distances, then it means that it will be just one line on the plot. And then you need to make only one test. So in this case, you don't need Bonferroni correction. Okay. So let's sum up and make like an algorithm, step-by-step algorithm based on this triangular rule. So this is how to build a model. First of all, you need to compute mean and standard deviation of your training set. Yeah, keep it as it will be vectors. That's why I have bold letters here. So for every variable, you have one value of mean and one value of standard deviation, right? Then you standardize your data. Of course, if you need standardize, otherwise you just mean center it. It's up to you. Then we compute we need to define how many components, of course, and then for given number of components, we compute vector with score distances, vector with orthogonal distances for the training set. And then based on these values, we compute these two parameters, right? The scaling factor and the degrees of freedom. Yeah. Then after that, we use these parameters to scale the distances and compute a vector of full distances. And based on the vector of full distances, we also compute the critical limits. That's it. Now we save all these things. And what we need to save, of course, the estimated parameters here, the critical limit here, and of course, we need to save average and standard deviation. Now, when you have a new set of variables, a new set of observations, for example, you have just one object or several observations. First of all, you need to scale them and center them, but it's important that you use, it's similar to PCA, you use M and S you computed for the whole model, for the training set. Right? After that, you do the projection, so it means that you compute scores and residuals, metrics with scores and metrics with residuals for your observations. And then based on these two matrices, you compute the distances, right? The Q distance and H distance. I use this letter N, index N, because it's like new to differentiate it from what we had before. And since you can see it's not bold, I assume that we have only one object here, but it doesn't really matter. Then based on this, two, and then also on the parameters we computed before, we compute the full distance. And then we simply compare the full distance with the critical limit we calculated before, right? If this is smaller than critical limit, we accept this object as a member. If it's not, then we reject this object as a stranger. So you can see it's very simple, actually, algorithm. Mostly it's a PCA decomposition and the projection of new objects to the PCA model.